So what I have here, this is what you guys are going to use. So this is your light source, and it's projecting a number 4. Okay? You can spin it, you can get an L, you can get hash marks, which are boring because you can't tell what's up or down, or you just get just a bright light itself. But what we're always going to use is number 4. So
Yes.
I got this set up, and we're going to use these tracks because it allows you to measure distances easily based upon where things are. So you don't have to have like a separate meter stick. So what I have here is a 10 centimeter double convex lens. Okay? I know it's a lens because I can see through it. It's not a mirror, nothing's being reflected. So the 10 centimeters tells me what the focal length is. Okay? So this is an intrinsic property of this. So there's nothing to measure. This is just boom, it's 10 centimeters, that's the focal length. You got other ones that are like 20 centimeter focal length. So depending upon where I put this, so this distance from the light source to the lens, is that my image distance or my object distance?
Image.
Which one? I heard both. That's why I dropped my head in pain. Is it image or object?
Object.
Object. Okay? Because I heard both. That's why I was going like, no. Okay? So this is how far the object is from the light source. Okay? Now, over here, I've got a screen and I'm going to adjust that position. You'll notice that depending upon where I am, this 4 looks very out of focus. But if I bring it closer, you'll notice that it reaches a point where that 4 is pretty much in focus. But if I bring it past that point, what happens?
Blurs.
It gets blurry again. So there's one distinct point, and it's kind of a judgment call, when that 4 is in focus. Now, the 4 that's projected is like this. What do you notice about the 4 that's on the screen?
Upside down.
It's inverted, okay? So this is what's known as an inverted image, but it's real. And it's real because of the fact that I can project it onto a screen. So if I can project an image onto a screen, it's real. So I would describe this image in 2 ways. I would say it's a real image, because I can have it show up on a screen, and it's inverted. So what that means is that as that light comes out, it hits this lens and it goes down. The bottom one hits the lens and it goes up. That's what allows it to get flipped. Okay? So sometimes you'll see images that are upright. Sometimes you'll see images that are inverted. Now, obviously, for those of you that wear glasses, do you want your glasses to invert the image?
No.
No, that would be really weird. It's like, when you put your glasses on, oh, it's in focus, but the world is upside down. Okay?
That would be cool.
No, it would not. Okay, that would be a train wreck. Now,
But they don't. There's no.
but I can change this. So what I have here to here is object image. Which one is it?
No, it just processes.
Object. The distance from here to here is
Image.
the image distance. Okay. Now, if I move this object distance, now notice that that's no longer in focus. But now I can find another point where it is in focus. So the other thing that you need to keep track of is what's known as the image height and the object height. So your object height, in this case, and this is what you're going to do in the lab, you are going to physically measure the dimension of that 4. Okay, like what is that distance? It's like 3 centimeters, whatever that is. Okay, so you can talk about object height. Okay, now you can also talk about image height. Now, looking at this, just a ballpark comparison, which one is bigger, the object height or the image height?
Objects.
Object, okay? This is bigger than what you see. So then we're going to talk about something known as magnification. And I know I'm throwing a whole bunch of vocabulary at you, and you're like, oh my God, it's like trying to drink out of a fire hydrant right now. So magnification basically refers to how does the size of that image compare to the size of the object. If they're the same size, what do you think the magnification is?
1.
1, okay? Nothing's gained or lost, okay? It's the exact same size. If this is smaller, if the image appears smaller than the object, the magnification is less than 1. If this looks bigger, the magnification is greater than 1, okay? So magnification gets you an idea of how big this is relative to this. So if I continue to change this, I move that farther out. Now, interesting thing happens. So when I'm really close, and if you look at a pattern, let me go through here, and then I might be too close. Okay? So when this is close, I've got a pretty big 4, right? If I move this further out, what happens to the size of the image? Okay, if I move this even further, then it's going to get even smaller. Now, you'll also reach a point with this, you can kind of see it. Okay? So right now, the 4 is out of image, but why do you think you see, you need to get on this side, or I guess you can see it from that side too. What do you think those horizontal lines are?
Those are there to measure the size of the object.
Nope.
They're the lights.
They're the lights from the front of the room. Okay? So now what's happening is that because of the fact that where I've positioned this, now it's taking the lights from the back, from the front of the room, and they're in focus, and that's why when I put my hand there, that gets blocked. So now not only can I have, now if you look at the lights back there, what do you think is true about that image distance compared to this? Much bigger, right? Because now my image distance would be from the lens all the way to the lights in the front of the room. So obviously if you're dealing with the telescope, guess what? What are you going to know about like your object distance?
It's huge.
It's huge, right? You're looking at Saturn, Jupiter, whatever, okay? That's a really, really, really big object distance. But obviously, let's magnify it so you can see it a little bit better. Okay, got that idea?
Yes.
Okay. Now, that's with a lens. Over here, similar type idea.
But the bigger lens.
Okay, so again, I've got a 4 that I'm projecting, and this is what's known as a split screen, okay? So this is a mirror, and I can take that and I can spin this around. So if I do this just right, if you look on, you kind of need to be on this side to see the 4. Okay, so get on that side. Get on that side. Okay? So what's happening is that the light is being emanated here. It's going through this split screen. It's hitting this mirror. That mirror is bouncing that light off of that, and you're seeing it on the screen. So this distance from here to here, object distance, image distance. Object distance. So in this situation, the object distance is much bigger than the image distance, okay? So get out of your minds right now that, the image distance has to be smaller than the object distance, okay? Doesn't. So I can take this mirror and I can adjust where that position is. Now, same thing is going to be true though. If I move this half screen, what happens?
The image loses focus.
It goes in and out of focus, right? So, but again, you would have to be told, hey, this is a certain focal length of mirror. So when that brings that into focus, now, what do you notice about the 4?
Still inverted.
It's inverted. So this is an inverted, is it a real or virtual image?
It's a real image.
It's a real image because I can project it onto a screen. So here's what I've got so far. That was a convex lens that was shaped like this. This is a concave mirror that's like this, okay? So one of the things I want you to get out of your minds right now is that, oh, convex lenses always produce like virtual images or there's no real standing pattern, okay? You will see that later on. But don't establish a pattern until I tell you to establish a pattern. Now, here's what I want you to do. I'm going to pass this around. This is a concave mirror. So what I want you to do is bring it up really close, and then look at it, and then put it further away, and then try to find yourself in the mirror farther away. Oh, there we go. Okay? And then see what changes. So you're here, look at it, and then put it further like at arm's length, and then see what you see. So this is going to be important. So look what happens when it's close to you, and then compare that to what happens when you're further away. And what you're going to see is that it's going to get blurry in between. Okay? So you're going to be, when you bring it close, you're going to be able to see yourself. Okay? But then when it's further away, you'll also be able to see yourself, but it's not going to look anything like it did when you were close together. Okay, so take a minute, pass that around.
Is the focal length like the distance to the convergence point?
It depends. It can be.
Okay.
This is weird.
Oh, wrong one. Where is? Hold on. Give me a second. I gotta find something. There should be a smaller one.
The focal distance is not
Basically,
Now, in contrast to that, so what's first being passed around is a concave mirror. You're going to see 2 different images. The next one I'm going to pass around is a convex mirror, which means it's going to be like that. So now, with the convex mirror, bring it close, put it further away, see if your image flips over.
Bird.
What?
Can I go to the bathroom?
Yeah.
Run away, run away. Bird, can I go?
Real or virtual? Now go.
Imagine if VR. Imagine if VR going to the
Cohen, what happened to you?
Cohen, what did you do?
This lecture is not going well for my brain.
Have you done
Oh, we're not even close to being done yet.
Yeah, I know, that's why.
Funny mirror make funny image. What are you doing?
Huh?
Funny mirror make funny image. Yeah. Here you go. Yeah.
no, he said don't make any patterns until he tells
Funny
you to.
mirror make funny image.
No, not yet.
Regular
What's your
mirror
thought
makes
on the
regular.
two-way mirrors?
It's not those like
Creepy.
wavy mirrors like
Dude, we should. Yeah, when are we gonna get to the like clown house mirrors?
It's really not. The math is horrible.
Okay, good. That's not good. Let's not do those. Let's not. I changed my mind.
Yeah, 2-way mirrors are just creepy.
What are we doing here?
Which one is this one?
Yeah, which one of those funhouse mirrors?
Let me get my notes.
I remembered any of it?
See that one?
Okay, so here's the pattern that I want you to begin to establish when it comes to mirrors. Okay? Here's a simple way to tell the difference between a concave mirror and a convex mirror. Convex mirrors only produce one type of image. So for those of you that are holding that convex mirror, what do you notice about the image? Is it flipped over or is it upright?
It's upside down.
What?
I'm just looking at meanings.
Whatever one this is.
You're
Okay.
so
If you have a convex mirror,
it's always up.
it's always upright, okay? Your convex mirror is always upright. Concave mirrors can produce two different types of images. One that's inverted and one that's upright. And you also will get into the magnification of this. So if you hold a mirror and you change its position and you see one image and then it gets weird in between and out of focus and then it forms another image, that means that that's a concave mirror. If you look at it and it only produces one type of image, it's a convex mirror. Okay?
Take the mirror.
So that's one of the patterns I want you to begin to establish. Okay, now, come over here.
Another visual?
Okay. So, hip. I know the roller coaster was kind of in the way, but this has a pretty short cord. So, what this is a ray box, generates 4 parallel light rays. So the first thing I'm going to do is I'm going to hold up, this is a lens, concave, convex. Concave, because you can like walk into it, okay? So this is a concave. So notice when I put the light on here,
Oh, that's cool.
what does the light do? Does it converge or diverge?
Diverge.
Diverge. Now, when it comes to focal length, this is one of the most important things that you need to remember. Focal length can be positive or negative depending upon the situation. And this is how you remember it in terms of people. If someone is, Alex, I swear, just stop. If someone's a positive person, do they bring people together or do they force them apart? They bring them together, right? So if a lens or a mirror brings the light together, that's a positive thing, and you have a positive focal length. If it's like this, where that light gets spread apart, now you're diverging that light. That's going to be a negative focal length. Now, so this was a concave lens. Now, here I've got also a lens which is going to be convex. Now, when I put this up here, now what happens to the light rays? They converge. So it's bringing it together. So is the focal length going to be positive or negative? Positive. Because the light's being brought together. So if you have a convex lens, the light gets brought together. If you have a concave lens, the light gets spread apart. Cool. Now, this is a mirror. Okay? Here's a curved surface. There's a curved surface. Convex, concave.
Convex.
Convex. Light comes out like this. Now, when I put this on here, ooh, what does it make the light do?
Spread out.
Ah, it makes it spread out. So it makes the light diverge. So would this be a positive or negative focal length? Negative, because the light's going out. Now, in contrast to that, I've got, this is also a mirror. Concave, convex. This side right here.
Concave.
Concave, like you're walking into it. So what do you think this is going to do with the light?
Converge.
That brings the light.
Don't forget to dress up for tomorrow's Spirit Day. It's versus Wild West. Choose to either wear your cowboy or surfer.
We don't do it.
Okay. So,
We're interested in doing both clubs. Don't forget to sign up and fill out your permission slip. See Ms. Mouse, be ready.
I'm sure
okay, so this makes it a little bit easier to see.